Imagine a self-driving car, effortlessly navigating a busy city street, or maybe a robot arm reaching out to pick up some object it's never seen before.
Hmm.
What's absolutely crucial for these machines, it's their ability to see in 3D, to understand depth, kind of like we do with our own two eyes.
Exactly. That spatial understanding is fundamental.
And this is where we get into the fascinating field of stereo vision in computer science, basically teaching machines to figure out depth from two slightly different images.
Mhm.
But here's the thing, the enduring challenge, despite, well, decades of incredible research, getting computers to reliably understand depth in new, totally unseen environments without tons of retraining. That's been a major hurdle.
It really has. That's the zero-shot generalization problem you mentioned.
Precisely. So our mission today is to take a deep dive into some really groundbreaking research from NVIDIA. It's a paper called FoundationStereo, Zero-Shot Stereo Matching.
A very important piece of work.
Yeah, it introduces what they call a foundation model
Right.
that promises to revolutionize stereo depth estimation, making it truly adaptable, truly robust in ways we just haven't seen before.
It's aiming high.
It really is. So get ready for some, aha moments. We're going to unpack what makes this breakthrough possible and how NVIDIA seems to have cracked the code on generalizable 3D perception for machines.
It's fascinating stuff, especially considering how long this challenge has been around in the field.
You're absolutely right. The whole idea of teaching machines to see in 3D isn't new at all. I mean, the very first stereo matching algorithm, that dates back almost half a century.
That's right. 1976, Mar and Poggio, that's where it really kicked off. And yeah, while computer vision has seen just extraordinary advancements since then, that core challenge you mentioned, zero-shot generalization, it always persisted. And just to be clear for everyone, this means a model trained on one specific set of data really struggles when you put it in a completely different environment or show it new types of objects, unless you fine-tune it specifically for that new scenario.
Right?
And why does this matter so much? Well, think about it. Imagine a robot trained in a super clean, simulated factory.
Okay.
Suddenly, it needs to navigate a messy, real-world construction site. Total chaos compared to the simulation.
Yeah, completely different.
Or think about augmented reality. Works perfectly in your living room, but then you step outside, and it just fails to place virtual objects correctly in the park.
Ah, I've seen that happen.
Exactly.
Yeah.
Fine-tuning these complex models for every single new scenario. It's just impractical. It's incredibly costly, sometimes impossible. It's really been a major bottleneck.
So it kept the tech kind of stuck in the lab, in a way.
In many ways, yes. Preventing it from really thriving in the unpredictable real world.
So, okay, here's where it gets really interesting for me. Why has this zero-shot generalization been so elusive specifically for stereo matching, especially when we've seen these incredible breakthroughs with foundation models in other areas like, image recognition or natural language processing? Those fields seem to have cracked the generalization code.
That is a great question. And it really comes down to the inherent complexities of stereo depth itself. It's a tricky problem. Previous leading stereo networks, while they were highly effective in specific domains, they had some pretty fundamental limitations.
Like what?
Well, many traditional methods would build these really elaborate cost volumes. Think of it like a 3D grid representing the likelihood of different depth values at each pixel.
Okay.
And then they'd use deep learning models like 3D convolutional neural networks or CNNs to filter that volume. Others use something called iterative refinement with recurrent modules like GRUs.
Right, refining the estimates step by step.
Exactly. Now, these approaches, they achieved amazing results on public benchmarks, but that was usually after being fine-tuned for that specific domain. They basically got a sneak peek at the new environment.
So not truly zero shot.
Not really. And they struggled to gather what we call non-local information effectively across the whole image. They just weren't designed to scale well to the massive diverse data sets you need for true generalization.
So, like you said before, specialized athletes, not generalists.
Precisely. They were champions in their specific trained domains, but they weren't versatile. And, it wasn't just the older methods. More recent approaches tried integrating transformer architectures. Transformers are great at capturing long-range dependencies in data.
Yeah, they're everywhere now.
They are. So they tried using them for something called unary feature extraction. That's basically the model analyzing each individual image, first looking at textures, edges, that kind of thing, before trying to match them up for depth.
Okay, makes sense.
But the problem was, in many of these attempts, the transformers often lacked the specialized structure that those cost volumes and iterative refinement provided. And it turns out that specialized structure is pretty crucial for getting high accuracy and stereo depth.
So the transformers alone weren't enough for this specific task.
Not in the way they were initially applied. And furthermore, many of the previous cross-domain generalization efforts, they often relied on relatively small synthetic datasets, like the SceneFlow dataset.
How small are we talking?
SceneFlow has only about 40,000 annotated training image pairs, which sounds like a lot, but for training a truly general foundation model, it's actually quite limited.
Right, compared to the datasets used for, say, language models.
Exactly. So that limited data, combined with those architectural shortcomings we talked about, meant these approaches couldn't really serve as true off-the-shelf solutions. They didn't have that strong generalizability we expect from other computer vision foundation models. The field desperately needed that versatile generalist for stereo depth.
And that's where FoundationStereo comes in. This NVIDIA research from Bowen, Matthew Trepte, Joseph Aribido, Jan Kautz, Orazio Gallo, and Stan Birchfield. It sounds like they aimed squarely at this problem.
Indeed. That's the core innovation. FoundationStereo is designed from the ground up as a large foundation model specifically for stereo depth estimation. And its explicit goal is achieving strong zero-shot generalization without needing any per-domain fine-tuning.
Okay, so out-of-the-box usability is the key phrase here.
Absolutely. That's the ambition, to generalize robustly to all sorts of diverse in-the-wild scenarios that traditionally just stumped existing models.
What kind of scenarios?
Well, everything from structured indoor environments like offices to unstructured ones like cluttered warehouses, complex outdoor scenes, driving scenarios, and critically, objects with really difficult properties.
Like?
Think textureless surfaces like white wall, highly reflective objects, mirrors, chrome, translucent things like glass or plastic, even incredibly thin structures like railings or wires.
Wow, those are notoriously hard.
They are. And it also needs to handle complex lighting, deep shadows, strong sunlight, big exposure differences between the two cameras. This really does aim to set a new standard in 3D perception.
Okay, this is ambitious. So how did the NVIDIA team manage to crack this code? To build something so robust and generalizable, where did they even start? It sounds like a huge undertaking.
It absolutely is. And you're right to ask where they started. It all begins with the data.
Yeah.
Their groundbreaking approach revolves around the FoundationStereo dataset, or FSD.
Okay, FSD.
The sheer scale of FSD is unprecedented for this task.
Yep.
It contains 1 million synthetic stereo pairs.
1 million, that's wow, compared to the 40,000 in SceneFlow.
Exactly. It's a massive leap in scale.
Huh.
But what's really academically significant about FSD isn't just its size. It's the quality and the diversity.
How so?
It was generated using NVIDIA Omniverse, leveraging RTX path tracing. This means incredibly photorealistic rendering. We're talking high resolution, typically 1280 by 720.
So very realistic looking images.
Very realistic. And highly diverse scenarios. Structured indoor-outdoor scenes, driving scenes, even this category called flying objects, which features randomized setups with highly diverse geometries. They used over 5,000 object assets, furniture, vehicles, robots, you name it, with randomized locations, scales, appearances. And crucially, it features realistic reflections and widely randomized camera parameters.
Camera parameters, like what?
Things like the stereo baseline, the distance between the two cameras, the focal lengths, the camera perspectives. Randomizing these is vital for making the model robust to different real-world camera setups.
Got it. So huge scale, high realism, lots of diversity.
But here's a really innovative detail, a core academic contribution they made. The automatic iterative self-curation pipeline.
Self-curation, what does that mean? Why is it needed?
Great question. So while domain randomization, that process of varying everything, is fantastic for creating diversity, it can inevitably introduce ambiguous or just plain unhelpful samples.
Those bad training examples.
Exactly. Think of severe texture repetition that confuses the matching process, or maybe reflections with very limited context, making the depth impossible to determine reliably. These bad samples can actually confuse the model during training.
Okay, so how do they fix that?
The self-curation pipeline detects these problematic samples. Specifically, they used a metric called BP2, basically, the percentage of pixels with a depth error greater than 2 pixels. If a sample had more than 60% bad pixels by this metric...
60%? That's a lot of error.
Right. If it crossed that threshold, the sample was deemed bad and automatically pruned from the dataset. Then, new samples were generated to replace them. They actually repeated this process iteratively.
So they cleaned the dataset automatically?
Yes, iteratively refining the dataset quality. This ensures consistently high quality and significantly enhances the model's robustness. It's a really clever way to manage the potential downsides of massive synthetic data generation.
So the big takeaway here isn't just more data, it's smarter, cleaner, more representative data, meticulously curated.
Precisely. That curation is a key innovation.
Okay, so they've got this incredible data set. Did they build the model entirely from scratch then, or did they leverage existing knowledge? You mentioned foundation models earlier.
Yeah.
Tell us about the side tuning adapter, or STA. This sounds clever.
It is very clever. And yes, they absolutely leveraged existing knowledge, which is pretty standard practice in foundation model development now. You don't want to reinvent the wheel entirely.
Makes sense.
So the STA's main job is to help mitigate the sim-to-real gap, that persistent problem where models trained on synthetic data don't perform quite as well in the real world.
Right, the gap between simulation and reality.
Exactly. The STA does this by adapting rich monocular priors from another model called Depth Anything V2.
Depth Anything D2, what's that?
It's another powerful vision foundation model, but it's trained on a massive scale of real monocular images, single images for depth estimation. So it already has an excellent understanding of 3D structure from just a single viewpoint learned from real-world data.
Ah, so they're borrowing knowledge about depth from a model trained on real, single images.
That's the core idea. And the way they designed the STA is simple but really effective. They use a standard CNN to extract features from their stereo input images. Then, they smartly concatenate a downscaled feature map from the frozen final output layer of Depth Anything V2.
Frozen? Why frozen?
That was a crucial finding in their research. They discovered that keeping the pre-trained Depth Anything V2 model frozen, meaning its weights weren't updated during FoundationStereo's training, was essential.
What happened if they unfroze it?
It actually corrupted those valuable pre-trained monocular priors. Performance got worse. It highlights how carefully you need to leverage existing foundation model knowledge. You want to tap into it without disrupting what it already knows.
So it's like giving the stereo model a cheat sheet based on real-world single-image depth understanding.
That's a great analogy. It gives it a huge advantage in understanding 3D structure without having to learn everything from scratch just for the synthetic stereo pairs.
Okay, amazing data set, clever use of prior knowledge. Now let's get into the core architecture. How does it actually process all this information to figure out the depth? You mentioned something about an attentive hybrid cost volume. That sounds complex, but important.
It is central to the model, yes.
Mm-hmm.
The attentive hybrid cost volume, or AHCF, is where they made some really fundamental breakthroughs, particularly in handling the computational cost of stereo matching.
The cost volume being that grid of depth possibility.
Exactly. Processing that grid, especially for high-resolution images with large depth ranges, used to be incredibly memory-intensive and slow. The AHCF innovation is all about achieving long-range context reasoning, letting the model see the bigger picture across different depth possibilities, but doing it with unprecedented efficiency.
How does it manage that?
It has two main components working together. First, the hybrid cost volume construction itself. It intelligently combines two ways of comparing the left and right images: group-wise correlation, which is good at measuring similarity, and the concatenation of the unary features from each image.
Unary features. Those are the ones that include the info from Depth Anything V2 via the STA, right?
Precisely. That concatenation is crucial because it preserves those rich unary features, including the monocular priors, allowing them to be directly compared across different potential depth values or disparities.
Okay, so builds a smarter cost volume. What about processing it efficiently?
That's the second highly innovative part: 3D axial planar convolution, or APC, filtering. This tackles that memory bottleneck head-on.
Oh.
Standard 3D convolutions, which were often used in older models to filter the cost volume, are just computationally very heavy. Trying to use larger kernels, like 5x5x5 to see more context, it became unmanageable, even on powerful GPUs like an 80 GBB A100.
So a dead end for scaling up.
Pretty much. Their solution APC is really elegant. It decouples a single 3D convolution into two separate, much lighter operations. One works over the spatial dimensions, height and width, and the other works only over the disparity or depth dimension.
Ah, breaking it down, like a specialized 3D separable convolution.
Exactly. That's a great way to put it. It significantly reduces memory consumption, but still allows for much larger receptive fields along that crucial disparity dimension. Their experiments showed benefits up to a disparity kernel size of 17, which was previously unthinkable.
Wow. That's a serious engineering and academic contribution for scalability.
Absolutely. It retains the representation power needed but makes it feasible for high-res stereo. And within the AHCF, there's another key piece, the disparity transformer, or DT.
Okay, transformers again, but used differently here.
Yes, used in a very novel way for stereo. While others use transformers for the initial unary feature extraction, FoundationStereo applies a transformer directly to the cost filtering process itself.
How did that work?
The DT performs full self-attention over the entire disparity space within that 4D cost volume. Using tech like flash attention makes this computationally feasible.
Full self-attention across all possible depths. What does that achieve?
It provides incredibly powerful, long-range context reasoning. Think of it like the model being able to instantly compare a potential depth match at 1 pixel with all other potential depth matches across the entire image, helping it resolve ambiguities.
So it sees the global depth picture, not just local patches.
Exactly. It's much better at resolving tricky areas like textureless regions or repetitive patterns compared to just using convolutions or transformers on the initial features. It's a fundamental change in how the model reasons about the relationship between the left and right images.
More efficient, sees more context. That sounds powerful. Is there anything after the AHCF?
Yes, there's this final refinement step. After the AHCF produces an initial disparity prediction using a technique called soft argmin on the filtered cost volume, the model employs iterative GRU updates.
GRUs, those recurrent units again.
Right, there are 3 levels of these updates. They progressively refine the disparity map using context features, including those adapted by the STA, to guide the process. This helps avoid getting stuck in suboptimal solutions and speeds up convergence to the final accurate depth map.
Okay, so a multi-stage process. Amazing data, leveraging priors, innovative cost volume with APC and DT, and then iterative refinement. That's a lot of innovation packed in.
It really is a comprehensive approach.
So the million-dollar question, does it actually work? What are the real-world results of all these deep academic and engineering steps, especially in those tough zero-shot scenarios?
The results are, frankly, quite remarkable. FoundationStereo achieves truly strong zero-shot generalization. Meaning, when tested on standard public real-world datasets like Middlebury, E3D, Kitty12, and Kitty15, without any fine-tuning on those datasets, it consistently outperforms numerous existing methods. And that includes very strong established methods like Stereo++, Graph Stereo, IGV, and others.
And those other methods were often fine-tuned on that data.
Many of them were, yes. They had the advantage of seeing data from the target domain during training. FoundationStereo beating them in a zero-shot setting is a huge testament to its fundamental generalizability.
That's impressive. What about leaderboards?
It dominates there, too. The fine-tuned version of FoundationStereo, where they did allow it to train briefly on the target domain data, ranked first on both the E3D and Middlebury leaderboards when the paper was submitted.
First place. By how much?
Significantly. On E3D, for instance, it reduced the error rates by more than half compared to the previous best methods. And interestingly, even its zero-shot performance, without seeing any E3D data, was comparable or even better than some leading methods that did perform in-domain training on E3D.
Wow. So even without the fine-tuning, it's competitive with specifically trained models.
In many cases, yes. And even back on SceneFlow, the synthetic dataset it was primarily trained on, it outperforms previous work by a large margin. It reduced the best previous endpoint error, or EPE, from 0.41 down to 0.33. That just shows the overall effectiveness of the model design itself.
And what about the dataset, FSD? Did that help other methods too?
That's another important point. The FSD dataset itself is proving to be a significant contribution. Their ablation studies clearly show that training FoundationStereo with FSD gives much better results than using just SceneFlow. But more than that, they also tried training other existing methods like IGEV on FSD instead of SceneFlow. And guess what?
Their performance improved too.
Significantly boosted on the real-world benchmarks. It demonstrates the high quality and general utility of the FSD dataset for the entire research community. It's not just benefiting FoundationStereo.
That's great to hear. Good data lifts all boats. What about visually? Does it handle those tricky and the wild cases you mentioned? Reflections, transparency?
Qualitatively, the results are very compelling. It shows superior performance on all sorts of challenging real-world images. Complex reflections, translucent objects, repetitive textures, difficult lighting. It handles them much better than previous methods. For example, there's a dataset called Booster, specifically designed with lots of shiny, specular, and transparent objects. FoundationStereo achieved an EPE of 2.2 on it.
2.2? Is that good?
It's drastically better than previous competitive methods, which had errors ranging anywhere from 6.6 all the way to 22.7.
Huge difference. Okay, that really validates its real-world robustness.
It does.
This truly highlights the transformative power we're seeing with these foundation models, doesn't it? Providing an off-the-shelf solution for something as complex as scenario depth, one that's robust, accurate, and ready for diverse unseen environments. It's a big step.
It is. However, the researchers are also upfront about current limitations in their paper's conclusion.
Oh, like what? Still room for improvement.
Always. First, efficiency. The model isn't yet optimized for speed. Processing a standard kitty-sized image takes about 0.7 seconds on a powerful NVIDIA A100 GPU.
Okay, so not quite real time for, say, a fast-moving car yet.
Not yet. But they suggest future work could definitely explore techniques like model distillation or pruning techniques commonly used to speed up other large vision models to improve the speed and memory footprint. That's crucial for practical deployment.
Makes sense. Anything else?
Second, dataset gaps. While FSD is massive and diverse, they note it still has a relatively limited collection of fully transparent objects, like clear glass with no reflections.
The really tough stuff.
Right. So enhancing robustness for those extreme cases might require augmenting the dataset with an even larger variety of transparent objects in future versions.
Okay, so ongoing work on speed and even trickier materials. That raises a big question for me. As these powerful foundation models for depth estimation get faster and even more capable, what kinds of new applications might we start seeing? How could this fundamentally change how machines interact with our world?
Well, the broader vision here is pretty exciting. Having generalizable foundation models like this really lowers the barrier for adopting stereo estimation in practical applications.
Because you don't need to fine-tune for every situation.
Exactly. Think about advanced robotics. Robots that can navigate truly complex, unstructured spaces, disaster zones, cluttered homes, dynamic construction sites much more reliably.
Yeah, that requires robust depth perception.
Or think about truly immersive, augmented, and virtual reality. Experiences where digital objects blend seamlessly with the physical world because the system understands the 3D geometry of your surroundings with unprecedented accuracy. No more virtual objects floating weirdly or cutting through real ones.
That would be a game changer for AR/VR.
It really would. This kind of research is paving the way for machines to understand depth with a versatility that starts to mirror our own perception. It's opening up a new frontier for intelligent systems, potentially bringing reliable 3D vision into the mainstream.
So wrapping up today, we've taken a really deep dive into NVIDIA's groundbreaking FoundationStereo, a true foundation model for stereo depth. We've seen how its unprecedented zero-shot generalization, its ability to work in new places without retraining, is enabled by, well, a whole suite of innovations.
Starting with that massive, high-quality, self-curated synthetic dataset, FSD, created using Omniverse.
Right, and then that clever side-tuning adapter, the STA, that intelligently borrows knowledge from real-world single-image depth models like Depth Anything V2.
Don't forget the core architecture, the attentive hybrid cost volume, or AHCF.
Yes, with the memory-efficient axial planar convolution, APC, solving that scaling bottleneck.
And the powerful disparity transformer providing that crucial long-range context reasoning across all possible depths.
It's really a combination of smart data, leveraging prior knowledge, and fundamental architectural innovation.
That's a great summary.
And this isn't just, papers and benchmarks. This means machines can now potentially see and understand 3D environments with far greater accuracy and adaptability than before. That impacts everything from self-driving cars hopefully becoming safer and more capable, to industrial robots performing more intricate tasks, and maybe even the immersive digital experiences we'll have in the future.
The potential impact is huge.
So here's a final thought for you, our listener. Think about how crucial accurate depth perception is in your own daily life. Just navigating a crowded room, reaching for a coffee cup without knocking it over. It's second nature to us. What new possibilities truly open up when our machines can perceive depth with this kind of unprecedented accuracy and generalization, even in environments they've literally never seen before?
It's definitely something to ponder.
Stay curious and keep exploring these incredible advancements happening at the intersection of AI and machine perception. There's so much more to come.